All right, good morning. Dang, this room gets emptier and emptier all the time. It's you guys are just the hardcore students that actually come to class. All right. So, get your time in at those SI sessions, right? We don't have that many more of them. We got our final coming up. One thing that I just did is that I converted all three of the computer portions of the exams into practice exams. So if you go into the quizzes, you can find, exam 1, multiple choice dash practice. So you can go in and repeat those just for studying. You won't get any points for them, but it's the same exams that we went through before. The answers will be shuffled. So if you don't, I don't think it's not set up to tell you what the right answer is, but it will tell you if you got them right or wrong. So if you got one wrong, repeat it and figure it out. Okay? All right, so that's to help you study for the final. All right, so yesterday we started into chapter 24, is on carbonyl condensation reactions. We talked about how this is really the culmination of all of our carbonyl chemistry. And in these reactions, the carbonyl groups will act as both the electrophile and the nucleophile. We looked at the aldol reaction yesterday, and these are condensation reactions between aldehydes or ketones. Okay, and we saw that we could actually do cross couplings too between different molecules. The things that we had to deal with in those cases, though, is if we had both components of the reaction, if they could both form enolates, if they both had alpha protons, then we oftentimes would get a mixture of products. So we looked at the aldol, and these in general give beta hydroxy carbonyls, so aldehydes or ketones. Okay? So today what we're going to do is we are going to look at what's called the Claisen reaction, and this is a condensation reaction of esters. Okay? So one main difference is that if we think about the aldol where we're doing ketones and aldehydes don't have a leaving group, right? So the aldol reaction was an addition reaction. Okay, there's still a little too much talking. The esters, of course, esters have a potential leaving group attached to them, and so esters will, the Claisen reaction will predominantly be a substitution reaction. An acyl substitution reaction. Okay, once we get to that, we're going to go on and we'll talk about what's called the Michael-Ration reaction. I don't know who did that. The Michael reaction is the reaction of a enolate with an alpha-beta unsaturated carbonyl. Okay, so remember, alpha-beta unsaturated carbonyls can do either 1,2 or 1,4 addition. All right, so we're just going to use a different version of a carbonyl electrophile by putting the extra double bond. I don't think we'll probably get to it today, but this Robinson annulation. So an annulation is a ring-forming reaction. And the Robinson annulation is kind of interesting because it combines a bunch of different steps where we start out with this Michael reaction and then we essentially do an aldol reaction after that, all in the same reaction. So it's kind of a cool one. All right, so that's where we're headed. Questions? All right, let's do the clicker. All right, so the Claisen reaction is our next. All right, so like I said, the Claisen reaction is the condensation of two molecules of an ester. All right, so the first thing we're going to do is to deprotonate the alpha position. Okay, so here's the alpha position. I wrote hydroxide is the base. Is that a good base for this reaction? Right, hydroxide would not be such a good base for this. Why? Because it can do a base hydrolysis to give us the carboxylic acid. So we don't want to use the hydroxide for this. Whenever we use an ester, remember the base that we tend to use is the alkoxide, which corresponds to the ester. So methoxide, we do this in methanol. Okay, so when it deprotonates, the base, the conjugate acid of the base is our solvent. Okay, so we can remove the alpha position, so we're going to essentially form an ester enolate. So let's go down this way. So all of this stuff is really in equilibrium. Okay, and here's the enolate. Let's just remind ourselves that this has a resonance structure which would move the electrons up onto the oxygen. Okay, so this is, an enolate. I don't think we've drawn an ester enolate before. We had enolates of ketones and aldehydes. Okay, so this is the ester enolate. And so just like in the aldol condensation, the enolate of the ester is going to react with the carbonyl of another ester. Okay, so it's the ester acting both as the nucleophile and as the electrophile. Okay, so these electrons come over here, attack the carbonyl. These electrons go up onto the oxygen and form a tetrahedral intermediate. Okay, I'm going to turn around that first ester. And we can draw this like we did before. O minus, OCH3, like this. Okay, so this is just really our tetrahedral intermediate. Okay, just like in every carbonyl reaction that we've done. All right, so this tetrahedral intermediate has a leaving group on it. All right, so these electrons can come down like this to reform this carbonyl, and the methoxide can leave. Okay, so it essentially reforms the base that we used at the beginning. Okay. And so that's going to give us, okay, I'm going to turn this around. Well, we'll just keep it the same. Like this plus methoxide. Okay, so this we could call a beta keto ester. Okay, so we have the ester, and on the beta position is a ketone. All right, now this is all in equilibrium, but this equilibrium will get kind of shifted toward the products because of an acid-base reaction. So this is similar to what we saw when we did the base hydrolysis of an ester. Remember, we got a carboxylic acid as the product and an alkoxide, and then it did an acid-base reaction to pull the reaction toward the product. So the same thing happens here. I'm going to loop back here, but what we'll really want is that beta keto ester is really going to be, depending upon pH, is going to be what we want, but what's going to happen here, remember that the alpha position between an ester and a ketone is more acidic than an alcohol is, or more acidic than water is. That means that the conjugate base of water or conjugate base of an alcohol is a strong enough base to deprotonate that alpha position. All right, and so what, let's see, that's not right, is it? That needs a C in there. Okay, I'm going to redraw this. Like this, and we have made this enolate. Okay? So the enolate is essentially not going to react farther. That enolate is less basic than the enolate that we start with, but what this does is it pulls the reaction all the way to the product. Okay, and stops over there. Yeah?
And that's just because it's a basic solution, essentially.
Right, it's just because it's a basic solution, and that alpha position of the beta keto ester is acidic enough that the acid-base chemistry is just going to push it that way.
So we'll say we want to keep the beta keto ester. So we just move into like an acidic condition.
Right, so what we would do, good question. So because this is really what we want, okay, the reaction is going to go all the way to the final enolate that I showed. But when we want to work up the reaction, what we would do is we would just add some water or some dilute acid into it, and it would just protonate that. We'd probably do some extraction, right? We could dissolve, with some organic and an aqueous acid layer, and we could extract the product, the beta keto ester, into the organic layer, once it's been protonated. Okay? So essentially that's what we're going to do. We're going to get to this product, and then in another step, we're going to say then we're going to add some dilute acid. Just enough to, or just a strong enough one even, just to protonate the enolate. We don't want to start ester hydrolysis or anything like that, right? But we can add some acid just to quench the reaction, just to neutralize it. Okay? Okay, so this is the Claisen. So when we do a Claisen, we go from esters to a beta keto ester. Okay? Remember, the aldol gave us a beta hydroxy aldehyde or ketone. Okay? So this is really a related compound to that acetoacetate, right? So even if you got this, we could alkylate again at that alpha position. We could hydrolyze the ester and do a decarboxylation, right? So we can do all of that same chemistry. All right, so let's just do another example. I don't think we have to draw out the whole mechanism here necessarily, but why don't you see if you can draw the product of this Claisen reaction. All right, so we can do just like we did with the aldol. I'm going to leave myself some room here. We can just redraw our ester. Oops. So, right, and the second molecule or equivalent of this ester is going to be attached to the alpha position. Okay? And at this point, we could also, just here, I'll just draw the second equivalent of our ester. I'll just draw another one of them over here. Right? And to make the product, all we have to do is, oops, that's not what I wanted to do, is erase this methoxy group and connect the alpha position directly to that carbonyl. Okay, because it's just doing an acyl substitution reaction. The nucleophile, this position acted as the nucleophile, this position acted as the electrophile. Okay, and because it was an ester, it has a leaving group, so we did a substitution reaction. Okay, if we're drawing the mechanism of this, then we want to remember that the other product would be ethoxide, and this equilibrium would shift all the way, it would deprotonate this alpha position. Okay, so if I ask you to draw the mechanism of the Claisen, I want to see the acid-base chemistry at the end. Okay, so that would be like this. We can just draw the same. Draw like this. And this would be the anion at this position. Okay, so we've just deprotonated that position. And if we want to get to the neutral product, then we just add some acid. Okay, we just neutralize. Okay? All right. Okay, so we can also do various cross reactions. So we can do enolates from aldehydes and ketones and react them with esters, and we can do various combinations of these two reactions that we've just looked at. So in this case, this would be kind of what they called a directed cross reaction, cross condensation, because for one, there's only a single reaction component that has an alpha proton. We can only form a single enolate. We're using a strong base like LDA, so we essentially irreversibly form the enolate, and then we add the electrophile to it. Okay, so we try to control which direction. We try to minimize just aldol condensation between the ketone, right? We want that enolate to react with the ester. Okay, so in this case, we are essentially going to deprotonate the alpha position, right? So we're going to form an enolate here, and this enolate is going to attack the ester carbonyl. Right, so we can draw out the intermediates here. So we form a tetrahedral intermediate. this, and then the methoxide is the best leaving group. Okay, it's the least basic. It's less basic than that ketone enolate. So these electrons can come down here. We can lose the methoxide, and we can form our beta keto. Well, this is a beta diketone now. Like this. Okay, when we do it in LDA, with LDA as the base, then we essentially use kind of a 1-to-1 ratio of LDA to enolate. So as we do this reaction, we won't, well, we have methoxide left. I guess we have methoxide, which would deprotonate that alpha position, right? So this is going to generate methoxide. So this would also have an equilibrium, just like the last one. I don't know if I can fit it in here. That would make the anion like this, and then we could reprotonate. Okay? All right, so we can do these mixed. Let's just look at I've got a. All right, so some of these are kind of interesting, I think, and kind of practical. All right, so they all start with the same ketone. Didn't have much imagination when I was doing this. We use LDA, so we form the ketone enolate, and then we add various electrophiles. Okay? In the top one, look at this electrophile. So this is like an ester, but it's also an acid chloride. Okay, so this is called methyl chloroformate. Okay, and because that chlorine, the kind of the acid chloride component of this is the best leaving group, we can get this to add or just substitute one time. And so if it just substituted for the chloride, what kind of a functional group will we get here then? Yeah, so we can add an ester on here. Oops. Like this. Okay? So in the next one, I'm using methoxide, and I'm adding it to, this is just methyl formate. Right, it's the methyl ester of formic acid. Okay, so what kind of a product do you think we'll get on this one? Not the alcohol, actually. So, well, let's think about, let's draw the intermediate first. Okay, so we're going to deprotonate here. So we're going to form this enolate. This is going to attack the carbonyl carbon. We get our tetrahedral intermediate. Okay, in this case, we have a leaving group. We have another leaving group up above too, but this is the only leaving group that we have is the methoxy group. So in this case, this can come down. We can lose our methoxy group. So this is like in the Claisen, because our ester is reacting as the electrophile. And we can add an aldehyde at that position. Okay? In fact, I remember this when I was learning this, they were going over this in a synthesis course I took in grad school, and what they said is that this, because it's this beta diketone, this would actually tautomerize to this. Okay. All right, we looked at beta dicarbonyls, and we said that how they had a pretty good component of enol. All right, so the last one, again, we're deprotonating, and this compound is called dimethyl. It's kind of like a diester, right? But a diester like that is called a carbonate. Dimethyl carbonate. And so what kind of a functional group do you think we're going to have that we added here? An ester. This. Okay, so we can add various kind of electrophilic carbonyl compounds like this. Okay? Questions? So, yeah.
There's two ways to form this product, right? It's, the top.
The top one. So the question was, is there more than one way to form this?
Because we make it using the acid chloride from carbon ester at the top reaction rate rather than the double ester.
For the top one, I didn't.
The top reaction and the bottom reaction result in the same product.
Yeah, they do. Yeah, so those are two different ways.
Is there a reason that we want to choose one reaction over another?
Yeah, good question.
Or is it just two ways to make the same?
I think it's just two ways to do the same kind of thing. We're going to see another way we could do that too in just a minute. It's fun to have multiple ways to do the same thing. But it's funner, even funner, if you know whether you should pick one or the other. So this just gives you two options, I think. All right, so like in so many reactions in this class, once we've learned the reaction is an intermolecular reaction, we imagine what we could do if we had two of the functional groups within the same molecule. Okay? So the top one is going to be an intramolecular Claisen. And of course, somebody else discovered that one. So this one is called the, oops, I think there's a C in there. No, that's not right. The Dieckmann condensation. Condensation. It's just an intramolecular Claisen. All right, so the first step is going to be to deprotonate one of the alpha positions. Okay, so it doesn't matter which one we deprotonate. So I'm just going to do this left one over here. So we're going to deprotonate here. We're going to move our electrons to the alpha position, and so we're going to form an ester enolate. So what kind of a compound are we going to end up with here? Yeah, there's probably going to be, oh, I didn't even draw enough carbons there, did I? All right, so it's a type of a Claisen, so our product has to be a beta keto ester, right? But this one is going to be formed from this anion is going to reach around here to react with the carbonyl at the other end of the chain. So we're going to form a tetrahedral intermediate, and let's see how big is that ring going to be that we're going to form. We're going to start with the alpha position, right? 1, 2, 3, 4, 5, 6. Okay? So we're going to be making a 6-membered ring. And let's see here. Like this. And I'm going to draw that up here. We have our tetrahedral intermediate right here. And attached to that is going to be the ester. All right, so I may have twisted it around. So essentially we've made that bond right there. Right, so this position right here was the enolate. And this position over here was the ester carbonyl, right? And we made a bond between those two. Okay, so then we have our tetrahedral intermediate. We have a leaving group, so this can come down like this, and the methoxide can come off as the leaving group. Okay, so I'm going to go over here. And so we still have our ester group over here. And right here, we have a ketone. Okay, so there's our beta keto ester. Right, so if we had one less carbon in our diester, we would have made the compound on the last slide, right? And so, of course, when we make this, if we get to there, we're in methoxide, so we would have the same equilibrium. It would deprotonate the alpha position between those to form an enolate, and we wouldn't get our neutral product until we quench or neutralize the reaction. Okay? Okay, so we can do a similar thing with a diketone or a dialdehyde. So this would be an intramolecular aldol reaction. Nobody got to have their name for this one. But we have several possibilities for this case, right? At least 2 possibilities, because we have 2 different alpha positions for each of those ketones. All right, so we could either deprotonate, let's just go ahead and draw these. We could deprotonate at this position, the methyl, or we could deprotonate at this position. Okay, so let's see what we would get if we did a cyclization from each of those positions. Okay, so if we do it in blue this way, okay, oops, the blue one is going to go down this way, and so what size of a ring are we going to get for this? Yeah, it looks like there's going to be 8. Okay, so I'm going to draw that ketone over here. We don't draw 8 that often, do we? All right, and so that went to, here would be our tetrahedral intermediate. Right, and we would have formed this bond right here. Okay, so if we did this, then that would, this would be in equilibrium, this would react with water, right? This could protonate, and we would get our aldol product. OH and methyl. Okay, so what if instead the reaction happened by the red arrow? Then what would we get? Okay, how big would the ring be? 6. All right, so we would have a 6-membered ring. Right, and if this is the alpha position, we'd have a ketone like this. And here would be our tetrahedral intermediate, which we could then protonate like this. And we would get this product. Okay, both products are beta hydroxy ketones. All right, which one of those do you think would be more favored? The 6-membered ring, right? A 6-membered ring forming it is much more stable. 8-membered rings start to become much more strained. Okay, so this is going to go to whatever the more stable ring size is. Okay, so in a practical sense, this kind of cyclic or intramolecular aldol reaction is essentially good at making 5 or 6-membered rings. Okay, 8 or 7 or 4 or something like that are not so good. Okay, yeah, question.
Is like the 8-membered ring a minor product, or did you start?
Yeah, good question. I don't know. Yeah, I think you'd get very little of it, but I can't absolutely say there wouldn't be any. Okay? And then, of course, we could, if we heat this up a little bit, we can get it to dehydrate as well, right? And so we could get rid of the alcohol and would form a double bond right here. Right? Just like any of the aldol reactions. All right, everybody follow that? So we could, do the same analysis if we made this ring size, this ring 1. Well, if we made the diketone 1 smaller, right, then what would the possibilities be? Right, either 5 or 7, right? So then the 5-membered ring would be favored. Okay? Or if you got even smaller, let's see if the chain had a total of 6 carbons, then you could do the enolate from the methyl group around to the carbonyl to make the right ring size. Okay? Are you guys probably not following me there? So for example, there. Don't. So if we had this, 1, 2, 3, 4, 5, 6. If we had this ring size, right, then the most stable would be if we formed the enolate over here, and then this reacted with that ketone, because that would form a 1, 2, 3, 4, 5, 6-membered ring. Or if we had that even 1 smaller, again, we could form an enolate here, and that could form a 5-membered ring. So this would be 6-membered. This would go to a 5-membered ring. Okay? So there's a few different options there. All right, so on Monday, what we'll do is we'll finish up this chapter, the Michael and the Robinson. I didn't really put any synthesis examples in the notes. I'll try to think up of a couple of those. Where we're going after that is chapter 24 is on amines. Okay, but I think the main thing that we're going to review on amines is just kind of a little bit of acid-base chemistry and stuff. We're not going to look at a bunch of reactions of those. Okay? All right, so have a good weekend.